Thanks to all who are calling in on time. We have about 20 participants so far. I'm going to give people another minute before we officially kick things off.
Okay, I'm gonna grab some water real quick. Yeah, I think we're about to get started.
Thank you again for all calling in, especially during these unusual times. We're going to be trying to hold at least this first of our typical TAP colloquiums virtually. If you run into any technical difficulties, reach out to me, KG Klein at arizona.edu, and we can attempt to fix it on the fly. But today's speaker that we have coming all the way from the University of Chicago is Dr. Colby Haggerty. He is going to be talking about ion acceleration associated with plasma shocks. He got his undergraduate degree in physics from the University of Scranton, and then went to the University of Delaware to study magnetic reconnection using a variety of different numerical tools, specifically PIC simulations. He continued there, expanding into turbulence for a postdoctoral year with Bill Matthews, and then now has been a postdoc at the University of Chicago, working with Damiano Caprioli, working, I believe, on the material he's going to be talking about today. And then will be in the fall moving to the University of Hawaii as an assistant professor at their Institute for Astronomy. So we are going to have people hold their questions either till the end or put it up in chat, and we will then attempt to answer them at the end. If you do have a question that arises during that end question and answer period, either press the raise your hand button or send a chat and I will unmute you and we'll go from there. So without any further ado, I'll pass it over to Colby.
Great, so thank you so much for having me, guys. I'm happy, it sounds like I'm the first person to do this through Zoom, so hopefully there won't be too many hiccups. But today I'm going to talk about ion acceleration in collisionless plasma shocks, and in particular new perspectives on this kind of idea from kinetic simulations that I've been doing. And so this talk can be broken up into kind of three principal parts, just so you have an idea of kind of where I'm going with all this. The first is a background for collisionless plasma shocks. What are they? Why do I care about them? What's the real major problem that we're trying to solve? In particular, how do collisionless shocks produce energetic particles? I'll do a little bit of background. If any of you saw my talk at Shine this last year, you'll probably it'll be a little bit of a repeat for the background information. I'm going to talk about Fermi acceleration and the basic idea behind diffusive shock acceleration. Then we'll move on to kind of more modern theories that make up how people like to think about astrophysical shocks, and in particular how cosmic rays or these energetic particles that they produce can actually feed back onto the shocks themselves and change the hydrodynamics. And then I will show you some observations that show there is a clear tension or a clear disagreement between observations and this linear theory, and then, or nonlinear theory, excuse me, and then I will bring in simulations and the work that I've done so that I can explain why this tension exists and kind of give a resolution between what people think shocks should be doing and what observations are seeing shocks do. And that'll lead us to the last part, the new perspectives on particle energization and kind of back reaction. So I'd like to start with just kind of in a very basic sense, what is a non-relativistic collisionless shock? So we kind of have three terms here. The first is non-relativistic, which all that means is that the shock, which is a blast wave that moves out from some explosion or something, or some interface of two sets of bulk flows, is non-relativistic, so it's significantly less than the speed of light. Now that doesn't mean the energetic particles that it produces are necessarily that way, but the bulk flow is. Second is collisionless, and so principally all the work that I'm interested in is collisionless plasma. And what I mean by collisionless is essentially that the discontinuity associated with the shock and the dynamics over which we're kind of interested in studying, the mean free path of collisions is much larger than the width of the shock or something like that. And so kinetic plasma physics, where the magnetic field and the electric field are really the important parts that are actually going to inform how particles are accelerated. And then shocks are shocks. It's a rapid change of the bulk flow between one and to the other. So why should we care about collisionless plasma shocks? Well, there's two kind of important things. The first is that they are ubiquitous in space and astrophysical plasmas. So whether you're looking at heliospheric plasmas, like the Earth's bow shock or interplanetary shocks, you see these shocks pop up over and over, and you see energetic particles, non-thermal particles, and emission associated with them. Now, if you go further away from the Earth and you look to galactic sources like stellar bow shocks, novae, and supernova remnants, again, you see the same kind of structure pop up where you get kind of this discontinuity, and you get basically kinetic energy being turned into non-thermal particles and other types of emission. Or if you go even further out from galactic to extra-galactic sources, whether it's radio supernovae, Aegean lobes, or intra-cluster shocks, you can kind of see the same thing. And so ultimately, the question that I'm really interested in and what I'm trying to solve is, at all of these shocks, why do we see signs or evidence of non-thermal particles and emission? And that's sort of what this talk is geared towards, trying to explain why that is and kind of the details of that. So I want to take a second and talk about the basic kind of background and the language that surrounds collisionless plasma shocks. Just because not everyone thinks about shocks every day like I do, and so I think it's good to make it very clear and explicit what all the terms that I'm going to be using are. So here's a picture of a supernova remnant. You had some kind of stellar explosion in the center that produced this blast wave, and you can see over many, many years, this shock wave propagated outwards with this thin discontinuity along the edge of the shock. And so typically we define the shock by two regions. One region where the shock has not reached yet and the plasma is still cold and the density is still low. We call that the upstream region, and we'll be giving that a subscriptor either 1 or 2. And then here, after beyond the discontinuity, you have a downstream region with a larger density and larger temperatures. And what we know in physics is the frame that we see a phenomenon occurring in is not necessarily the easiest frame to mathematically analyze it. And so typically what people who think about shocks a lot do is, instead of doing it in the explosion frame or the lab frame or whatever, you jump into a frame riding with this discontinuity, with this red line corresponding to the shock. And so now, instead of having this downstream plasma flowing out very quickly, you have an upstream plasma that's coming at you very, very rapidly. And then the downstream is this green region is traveling away from the shock more slowly. And doing this has two important benefits. The first is that if the shock speed is relatively constant, then this problem becomes time invariant, which makes a lot of equations a lot easier. And it also has the added effect of looking quasi one-dimensional. So this is kind of the shock, this is upstream, this is downstream. Now, typically we can characterize the shock by two principally important variables or values. The first is the Mach number, which is essentially, if you are in the frame, if you're in the shock frame, this frame we're talking about here, you can calculate, well, what is this bulk flow velocity relative to a reference velocity in the system? And if you normalize that by the sonic Mach number associated with the pressure, or essentially the speed of sound, then that'll give you a characteristic called, a variable called the sonic Mach number. And if you normalize this bulk flow velocity by the Alfvén speed, which is a plasma physics velocity that's essentially, if you smack a magnetic field line, how fast will that signal propagate in a plasma? That's the Alfvén speed. You can normalize your bulk flow to that. And these two quantities are the sonic or the Alfvénic Mach numbers, and they effectively tell you how strong your shock is. If these Mach numbers are very large, say larger than 10, then you're said to have a strong shock. Typically in a lot of astrophysical situations, we see that these Mach numbers can be quite large. The second parameter that we can characterize the shock by is something called the compression ratio, which is essentially if you take the downstream velocity, again in the shock frame, and you take the upstream velocity in the shock frame, and divide it by the downstream velocity in the shock frame, that'll give you the compression ratio. And because of mass continuity, we know that that needs to be equivalent to the downstream density normalized by the upstream density. And so this is effectively a measurement of how compressed your plasma will get. So that's the basic idea of a shock. Okay, but how can shocks accelerate particles? We still want to know the real question, how do these things produce all of these energetic particles? Well, as we talked about that before, this plasma is collisionless, so we need a mechanism. You can't have direct collisions producing these energetic particles, so it has to be something else. And so kind of one of the more important, I would say, mechanisms for producing really energetic particles in collisionless plasmas is this idea that was proposed by Enrico Fermi in 1949 in a famous paper called On the Origin of Cosmic Radiation. And in the paper, he says, if you have some charged particle moving around and you have what he called a cloud or something like that, if you have this cloud moving and it can have the charged particle can have an interaction, then it will hit this moving structure, be reflected off, and get some increase in velocity. Of course, in the context of collisionless plasma, it's not really a cloud, but it's going to be a magnetic fluctuation or some kind of Alfvén wave or something like that. But the idea is if you have all these different moving fluctuations, particles can come in, knock off of them, and get an increase in energy. And the way to understand how that works can be understood pretty simply through a toy model. So let's consider this picture here, where we have a charged particle with this red sphere with some velocity v, and you have some moving fluctuation. Maybe it's a wall, maybe it's an Alfvén wave, whatever, that's going the opposite direction with some velocity v naught. And you want to ask, okay, how much energy will this particle gain? How much faster will the particle be going after it collides with this wall? So you can transform frames into the frame moving with this wall. So now this wall, this magnetic fluctuation is just stationary, and the charged particle has some new velocity v plus v naught. And now in this frame, all that happens is the charged particle comes in, has an elastic collision, and comes back out with the same exact velocity. But of course, if you transform back into the lab frame, you can see the wall's been unaffected, but now the particle has gotten a kick of twice the velocity of the wall. Of course, you can do this much, much more generally than just this kind of simple toy example, and you could also take it to the relativistic limit. And you can get an equation that tells you how much, what the change in energy of the charged particle should be after each one of these interactions. And I want to take a second and really break apart this equation because I think there's a lot of really important physics here that goes into particle acceleration. The first and probably the most important part is that the change in energy is proportional to the energy the particle has. And so what that means is that whether you have a KeV particle or you have a PeV particle, it is going to get the same proportional kick/increase in energy. And so what that means is this mechanism can continue to accelerate particles over and over and over again, no matter how energetic they get. Whereas if you had something that was not proportional, it would energize it to some value, and then it would take exponentially longer to continue to energize it more decades higher. So then the question is, well, what are the proportionality constants for this increase in energy? So we have this first term. You can notice both the terms depend on v naught over c, the velocity of the wall over the speed of light. And so, you know, because of relativity, those have to be decidedly less than 1. And so they're typically small numbers. And so you can already see that this is going to be a larger first order term and a larger second order term. And so this first order term, you can see there's also a cosine theta, which accounts for the fact that the interaction between the moving magnetic fluctuation and the charged particles don't have to be head on. But in fact, you could have a situation where your wall is moving this way or your fluctuation is moving this way, the particle comes in at an angle, goes back out at an angle where it won't gain as much energy, or in an even more extreme case, the wall is actually moving this way and the particle overtakes it and actually loses energy. And so the issue with this first order term, which is referred to as the first order Fermi acceleration term, is that if your particle velocities are uncorrelated with your fluctuation velocities, then this term will average out to 0. And it will have no real contribution for accelerating the particle. And then what you're left with is this second order term, which, if this is the important term in the equation, it's called second order Fermi acceleration, which is decidedly a smaller value, which means your particles will be energized less quickly or less rapidly. But of course, sometimes that's all you're left with. And this occurs from the fact that you expect to have more head-on collisions than tail-on collisions. So great, we have the basic idea of shocks. We have a basic idea of how particles are accelerated. So how do these two things go together? The way these two things go together is the process through which shocks can actually energize particles through a process called diffusive shock acceleration, or DSA. I'm going to be using that acronym a lot. And essentially the way DSA works is we have a little toy model here. You can see again our charged particle in red, and let's assume that this charged particle has a large enough gyro radius that it can jump over the shock, jump across the shock. Then it's going to come in, go downstream of the shock, and see a magnetic fluctuation. It's going to scatter off this moving wall, this magnetic fluctuation, and be sent back upstream. By going back upstream, it'll see another magnetic fluctuation where it will have another head-on first order Fermi acceleration process, and it will be sent back downstream, increasing the energy of the particle. And of course, this process can continue as long as the particle can go back and forth across the shock. And so this is the core idea of DSA. It takes the structure of the shock, which has some coherent structure of flows, and it puts in a particle that essentially ping pong balls back and forth between the upstream and downstream, allowing the particle to get a first order Fermi kick each time. And so this is important because it's doing that first order acceleration because you have some coherence between the bulk flows and the particle. You essentially have two converging walls that continues to energize the particle. An important note I want to mark right here. We talked about how these are collisionless shocks. And so I've put in little magnetic squiggles, these little sine or cosine waves or whatever. And I just want to remind you this for later that particles have to actually scatter off these magnetic fluctuations because they can't actually interact with the bulk flow. But this is the basic idea of DSA. And so one of the reasons DSA is such a powerful theory and why it's kind of quite well accepted for producing really energetic particles is because DSA and even the Fermi reflection process in general can naturally lead to power law distributions in energy. And the way to see this is actually pretty simple. So let's say instead of talking about our shock or anything like that, let's just say we have this magic black box energetic particle accelerator. So you have this structure here. And let's say every second or every couple seconds or whatever, you turn a crank. And two things happen when you turn a crank. The first is all of these particles are going to increase their energy in such a way that the energy gain is proportional to the energy the particles have by some proportionality constant g. When you turn this crank, you're also going to open a little window and some of the particles have a probability of escape, or more appropriately, some of these particles are going to have a probability p that they remain. Then you can write out really simply in time how many particles you'll have as a function of k cycles and what the energy each of these particles will have after k cycles. It's just going to go like p to the k, however many particles you had, and g to the k times however much energy they started with. Then you can very easily go and get rid of k in this equation, and you get a prediction for the number of particles you'll have in the box as a function of energy. And you can see pretty clearly that it just goes like e to some power, where you have the natural log of the probability of remaining over the energization factor. And so if this probability is constant and this energization is constant, which a shock and DSA satisfy, then this will be a constant value and you'll have a power law distribution. You'll have the number of particles dropping off like some e to some power. And so you can go through for a shock and DSA and you can calculate what this probability should be and what this energization should be. And you get that you should get a power law that goes like f of p, where p is now momentum instead of energy, that goes like p to the minus q. You can put in values, you can infer that the probability of remaining is going to be dependent on the bulk flow velocities, and the energization is going to be proportional to the difference in the two velocities. And what you can do is you can recast that in terms of one of those parameters we talked about before, the compression ratio, R. And so you get a prediction that DSA should produce power law spectra that go like p to the minus q, where q is 3r over r minus 1. And one of the really powerful things about this, and why astrophysical people might care a little bit more, is that for strong shocks, in which a lot of astrophysical shocks satisfy this condition, R asymptotically approaches 4. Like in hydrodynamic theory, the compression ratio for a Mach 10 and a Mach 1000 shock are almost equal. And they're both about 4, which means when you plug it into this equation, you get that your momentum spectra should go like p to the minus 4, or if you're doing it in energy space, it'll be e to the minus 2. they're equivalent. It just depends on how you want to look at it, which is great because if you look at the galactic spectrum of cosmic rays, it's not so far off from this. We see a power law spectrum, and it's not exactly e to the -2, but it's pretty close, and we'll talk more about that a little bit later in the talk and why we think there's actually this difference. So this is kind of the basic idea of DSA and how shocks can accelerate particles. And then observations seem to suggest that a pretty significant fraction of energy goes into these non-thermal particles. As much as 10 to 20% of the shock's energy needs to be donated into the energetic particle populations to account for the stuff that we're seeing. And so the next step in trying to understand this is, well, okay, if we're dumping almost a quarter of the energy into energetic particles, that's going to affect the shock. That's going to, this test particle calculation that we did for DSA isn't necessarily going to be appropriate. And we want to know, okay, what is the energetic population? How is that going to affect the shock itself? And so more modern theories of cosmic rays and shocks, or energetic particles and shocks, is this idea of cosmic ray modified shocks. And the idea is pretty simple. Here we have, again, kind of a toy model of a shock. And we say, okay, let's try to see what correction cosmic rays will have on this. So let's say that there's going to be some enhanced cosmic ray pressure downstream of the shock that doesn't really care about this discontinuity and is able to bleed back into the upstream. Well, then what you can see is that these cosmic rays are essentially going to exert some kind of pressure force on the upstream, which is going to slow the plasma down and pre-compress it. And this is going to lead to something called the precursor region. So we're using 0 for upstream, 1 for precursor, 2 for downstream. And so this precursor region and this precompression has some characteristic signatures that we might expect to see in observations. So the first is, how is this cosmic ray modified shock going to change the power law spectrum? And so what you can do, and I apologize for all the math, I know it's a lot, is that if we go back and we say, we call this discontinuity here the subshock, and then this the precursor region, and the Mach number is sufficiently strong, then you can get that the subshock should still be about 4. You can go further and you can rewrite the Rankine-Hugoniot jump conditions to basically include a cosmic ray pressure term, which we're going to be normalizing by the upstream kinetic energy density, and we're going to call that chi. And you can get that the total compression ratio should be basically R sub divided by this quantity, which says that for a cosmic ray modified shock, that total compression ratio should go up when you start to put more energy into cosmic rays. And so instead of having an R total of 4, like we talked about before, you might get an R total of 5 or 6 or 7 or something like that. And then what that says, before we argued that the power law spectra only depended on the compression ratio R. And so that means now that we have a new R based on Fermi acceleration and DSA, we should expect that we have a new power law index of Q that goes like 3.75 or 3.5. And so what that means is the DSA prediction, which said that the power law spectrum you have should go like P to the -4, now becomes something like P to the -3.5, P to the -3.75. And in cosmic ray language, we call that a flatter spectrum. So cosmic ray shocks and nonlinear DSA predict the spectrum should be getting flatter rather than kind of the steeper value it has. So that should be going up. So that's flatter, and if it goes down, then that's steeper. So cosmic ray modified shock predicts flatter. Great. And another kind of hallmark signature of this, of cosmic ray modified shocks, is that if you have these 3 distinct regions, you have kind of the upstream, the precursor, and the downstream, you're going to have one compression ratio between here and here because the plasma is pre-compressed, and the lower energy particle is going to undergo DSA feeling 1 compression ratio, R sub, and it'll have a steeper spectrum. And then as the particle gets more energetic, it'll be able to sample more of the shock with a larger compression ratio and lead to that flatter distribution that we talked about as well. And so this is another hallmark of cosmic ray modified shocks. The problem, of course, is observations. And so this slide goes, so what people have done is tried to look at supernova remnant observations to see how does the power law index. So this is the power law index inferred from gamma rays in both the GeV and TeV bands. And they were able to calculate what that essentially the power law index associated with these energized particles near shocks was. And what I'm going to do is I'm going to throw up what nonlinear DSA and what cosmic ray modified shocks predict the slope should be. And from this, you guys can probably see the problem that I'm trying to get at. So this blue area is all of that stuff I just talked about over the last 2-3 slides, predicts that the slopes we should see here should be in this blue region. But clearly across the board, we see a lot of situations in which that power law index isn't flatter, but is in fact actually steeper, which seems to be inconsistent with DSA theory, which is a bit maybe not great. And so the question is, so we see that this is happening for galactic supernova remnants. You can go and do the same thing with extra-galactic sources, in particular radio supernovae, and you get a similar thing that we talked about here, where most of the points are lying much higher than what nonlinear DSA kind of predicts. And so the question is what's going on is we have this theory that predicts we should see flatter spectrum, and we have observations that predict steeper spectrum. And so clearly there's something going on in the theory or in our understanding of observations that we don't quite have, because there's this tension, there's this this difficulty, there's this trouble against the two ideas. And so where I come in, and the work that I've really been doing at Chicago with Damiano, was to try to explain and understand where this comes from. And so typically, if you have a problem that's a bit too complex for just a linear theory or pencil and paper to work out, you can use simulations. And so what I really like to do, and what I've been doing for a lot of my career, is using kinetic plasma codes to try to solve these complex problems. And so before I get into the work and explain the resolution to this issue, I want to take a second and kind of introduce the basic tools that I use, the basic simulation tools. So the end-all be-all equation of modeling collisionless plasmas is something called the Vlasov equation. It's essentially this equation that tells you how this probability distribution function F is going to evolve in space and time, where F is the probability of finding a particle with a given velocity at a given location. And so you have, convection in real space, convection in velocity space, and time derivative equals 0. And so basically, if you want to understand a problem, if you can solve this equation, you can kind of understand what's going on, because this is telling us how plasma should evolve. And so, but this is really hard to do because it's a 6-dimensional phase space equation, which means a 6-dimensional grid, which is computationally really difficult. And so a way of getting around that is something called the particle and cell simulation. And it says, okay, take our distribution function F that describes our plasma, and let's break it up into a bunch of microparticles. And when I say a bunch, I mean a million or a billion, depending on how big your simulation is. And then what you can do is you can define your E and B fields on some teal grid, which you guys hopefully can see here. And then what you can do is once you define your E and B fields and you set up your particles to agree with some density system or some set of velocities that you care about, like a shock or like reconnection or whatever, you can go through and you can interpolate your E and B fields to each of these particle positions. When you do that, you can use the Lorentz force law to update all of these particle velocities and update all of these particle positions. Once you've updated all of them, you can reverse interpolate those values onto the grid points, and you can get J, your current density, and your charge density on your grid, which you can use as your source terms for a discrete version of Maxwell's equations. You can then redo the cycle a million or a billion times until you get a simulation that drops out. And this is the core idea behind the particle and cell method. Unfortunately, even this can still be computationally pretty expensive when you want to simulate really big things. And so another trick or another tool that we can use to try to keep some kinetic physics, but also model much larger systems, is to go to something called the hybrid approach, or hybrid simulations. And so what it does is it says, okay, these electrons, these little blue dots, because their mass is so much smaller, the gyro radius they make is much smaller. And because they're moving much faster, the time step you have to use to resolve it is much smaller. And so it's really computationally expensive to try to resolve these electron dynamics. So if we say, okay, we only care about the protons, or we only care about the ions, and we can just assume that the electrons are going to act as a massless charge neutralizing fluid that's just going to kind of sit on the background. And by doing this, it allows us to make our grid cells much bigger and our time steps much larger, but to only consider but still retain the kinetic physics of the protons. And so hybrid simulations are the approach that I'm actually going to be using to try to solve this problem. And then one little plug before I actually get to my work is a paper that we put out, I believe, late last year, which showed basically a new code we're calling dHybridR, or a modified code calling dHybridR, that allows for the fully relativistic dynamics to be retained in the code. Typically, in the historical formulation of hybrid, you have to throw out the displacement current in Ampere's law, and you do that by saying that your flows are much smaller than the speed of light. And so in practice, that means for most hybrid codes, you assume the speed of light is infinite, which means you can't have relativistic dynamics. But what we found is that if you have, for a very special set of problems, where you have a very low density population of relativistic particles, the approximation that this really needs is not necessarily that the particle velocities are much less than the speed of light, but the bulk flow velocities are much less than the speed of light. And so for problems with cosmic rays and problems like diffusive shock acceleration in collisionless plasma shocks, this is actually a really perfect situation because you have all these really energetic, in fact, relativistic particles, but the bulk flows are still non-relativistic like we talked about before. So that's dHybridR. If you're interested, please go read the paper and you can ask me about it and cite it and all that good stuff. So great. So finally, shock simulations, the stuff that I actually do. So just to remind everyone, we want to understand why observations are showing steeper spectra and theories for DSA are predicting flatter spectra, and try to understand what that is. So here are the simulations that I actually use to try to understand that. So just for everyone's kind of understanding, I have essentially a really, really long I have a really long two-dimensional box. So here's the y direction, here's the x direction. In the y direction is periodic, and in the left side of the x direction is a hard reflecting wall. So that particles hit it, they'll just be reflected back in the opposite direction. And then way, way off on the right, the box is much bigger than this, I promise. Particles are being injected to the left. So we initialize the system so that all the ions have some velocity going in the left direction. I think in all of this work, I'm only going to be showing you a Mach number 20, which means basically the particles are moving 20 times faster than the Alfvén speed towards the left of the wall. What's going to happen is they're going to come in, hit the wall, be reflected back upstream, and that's going to produce an instability, which leads to a shock. So I'm going to play this and you guys can hopefully see. I'm not sure how good the frame rate is. I'm going to take a sip of water while I let that go. And so what you can see is a lot of things. So first you can see the shock formation. So in the top, we were plotting the density. So you can see a lower density here and a compressed plasma here. And on the bottom, we also plot the out of plane magnetic field, BZ, which you can see a lot of kind of these magnetic fluctuations showing up. And so we can see the general structures that we talked about with the shock. We see an upstream and a downstream and compression and all that, but we can also see a lot of other stuff. So for one, we see a lot of magnetic fluctuation, which we haven't really talked about yet. But what we can also see is if this restarts, is all these little squiggles correspond to self-consistent particles in the simulation. And you can see that they come into the shock, are accelerated, and then scatter and are able to get back upstream, where they scatter off these magnetic fluctuations and come back downstream. So this movie shows, hopefully if the frame rates are good, shows that you can see the DSA process going on. You can see these particles in the shock. And just for everyone's clarification, the simulation is all started with a magnetic field, in the X direction, so it's a parallel shock. Oh, someone asked why the wall is moving to the left. So I boosted this simulation into the frame moving with the shock. So the wall is actually stationary, as you can kind of see. The wall is not actually moving. The window that we're looking at is moving. But that's a good question. Hopefully that makes it more clear. I promise that the wall is not moving in the actual simulation. Yeah, I just wanted to keep track of kind of everything that was going on in that way. Great, so what was I saying? Yeah, so what we can see is this DSA process we talked about clearly going on here. Oh, and I was going to comment that we initialize this. This is a parallel shock, so the magnetic field is pointing in the direction of the flow. So the flow is going this way, and the magnetic field is pointing just in the positive X direction. And there's a lot more physics when you start to change that, but I don't want to talk about it right now. We can talk about it at the end or afterwards. That'd be great. So great. So we see DSA. We see some of the basic physics we were interested in. So let's see. Okay, is this reproducing some of the theory about cosmic ray modified shocks? And so if we go forward, great. So if you calculate the distribution downstream of the shock, what you can see very clearly is that you reproduce the power law spectrum that we talked about. So here is a plot of the integrated distribution as a function of energy for a bunch of different times. And you can see that a power law tail does develop and continues to grow. So that's good. You can also go further and calculate, okay, how much energy is in this, this tail of particles. And you can find that if you plot, this is essentially a plot of the normalized energy in the cosmic rays, chi cosmic ray, excuse me. And you can see that it does in fact reach a little bit more than 10%. So that means a good chunk of the energy is being converted into cosmic rays and seems to be relatively constant throughout the simulation. Similarly, I also include the magnetic field, a normalized magnetic field, and see that a good bit of energy goes into those downstream magnetic fluctuations as well. But what this says is that, okay, well, we have the shock, we have these energetic particles, so we should see cosmic ray modified shocks. We should see something that's associated with that. And of course, we do actually. If you take successive cuts of the distribution function closer and closer to the shock, so this is a phase-based plot of the shock, this is the normal direction, this is the normal velocity, so you can see the shock here. If you take a cut here, you see this blue distribution. You take a cut here, you see this teal distribution. You take a cut here, you see this red distribution. So you can see the formation of a precursor. You can see the plasma slowing down and pre-compressing and actually getting hotter. So we do see one of the predictions of cosmic ray modified shocks. And what's further is if we plot the compression ratio, that R value, essentially the density over the upstream density, as a function of distance, each one of these colors correspond to a different time. We can see that as the shock propagates, the density, the compression ratio actually does go up. So here is the fiducial value of 4, and here is kind of an estimated value. We can see it's closer to 5 or 6. And so we do see a larger compression ratio. So that's, I guess, encouraging because it means that we're seeing what some of the theory predicted. But what that means is that, well, we see a larger compression ratio, so we should see a flatter spectrum, right? Because now R is bigger, R tote's bigger, we should see something that goes from 4 to like 3.5. But the thing is we don't see that. What we actually see is the opposite. So here is a plot of the distribution at different times. Again, each color corresponds to each density here. And what we've included is the DSA prediction, which we just said should be getting flatter and flatter. But if you plot the power law spectrum, what you can see is that consistently, it's much steeper. It's much steeper than what DSA predicts. So that's really interesting because what that means is our simulations agree with the cosmic ray modified shock theory that we should get larger compression ratios, but simultaneously they also agree with observations that say the power law spectrum should be steeper rather than flatter. And so what that means, hiding in the simulation somewhere, is the reason why you have this tension between these two understandings of astrophysical shocks. So the question is why? Why is that there? And so ultimately, after a whole lot of analysis, what we were able to figure out is that the source of this discrepancy is the amplified magnetic field. So here's another movie where I'm plotting, again, the out-of-plane magnetic field. And you can see that, and what we've kind of been continually seeing is that for the shock to process, you have these amplified magnetic fields. Essentially, because you have cosmic rays leaking into the upstream, they actually drive an instability that produces magnetic fluctuations that get compressed by the shock and become much larger in the downstream. And ultimately, as we talked about before, the Fermi acceleration process only cares about these magnetic fields. It doesn't actually care about the bulk flows, even though the bulk flows are the things we tried to use to characterize what the power law slope should be. And ultimately, these magnetic fluctuations are what I'm going to show you are why we have this deviation and why both of these things can be true simultaneously. And so, okay, well, we talked about how we need to know the magnetic field, the speed of the magnetic field is more important than the speed of the bulk flow. And so we want to try to quantify the quote unquote magnetic field. And so there's kind of, there's a few options that could be responsible for this change in the power law slope. It could be the upstream magnetic field, or it could be the downstream magnetic field. And in each of these cases, it could be that these magnetic fields are making it so the particles are not getting as much energization as Fermi might have predicted, smaller g essentially when we talk about that natural log g over natural log p, or perhaps these magnetic fields are causing the particles to escape faster, larger p. And so here what I've included is kind of a plot to give you an idea of which of those it's actually going to be. And so this is a time stack plot. The y-axis is the shock normal direction and the x-axis is time. So we're basically looking at a slice through our simulation at a bunch of different times. And so it's plotted in this way so that lines on this plot corresponds to velocities. So what you can very clearly see is the shock front, which is moving up and to the right, which means it has a positive velocity. But then what you can see is that in all of the downstream of this, you have these fingers, these structures of magnetic fields. So here's Bx, By, Bz, and B total. Bz is probably the easiest to see. You can see these structures that have some slope associated with them. And so traditionally, what is assumed in kind of the standard DSA and shock stuff that we talked about before is that downstream, the magnetic field doesn't really have a preferential velocity. Maybe it's going to the left, maybe it's going to the right through, you know, alphanic fluctuations, but ultimately it should be about whatever the velocity of the downstream is. But what we can clearly see is the magnetic field is kind of is moving along the direction that's kind of roughly associated with these black dashed lines, which correspond to the downstream alphane speed. And so that hints that maybe the downstream magnetic field isn't behaving exactly as we expect. Of course, we can be much more analytical than just looking at a time stack plot. We can look at the dispersion relation. So here I have the dispersion relation for the upstream, where essentially I just take an FFT window that's sitting in the upstream plasma. And then here downstream, I calculate with an FFT window sitting in the downstream plasma. And so in the upstream, what you can see is that you have sort of have power in magnetic fields in both directions. So this is omega and this is k. And of course, the sign of omega tells you which directions the magnetic fluctuations are going. And what we can see is that most of the magnetic fluctuations are actually going in the positive x direction, which is negative omega. We see we have directions going both ways, but there's a little bit more preference this way, which means, but the thing is that we know that it's consistent with the alphane speed, which has to be much, much smaller than u0, the velocity upstream. So we see these fluctuations, but we also see that they're consistent with the alphane speed, which is going to be relatively small to the fluid velocity. So that means these fluctuations are basically moving at the fluid velocity. Downstream, however, is a different story. You can see there's a lot of power in a lot of different modes because it's realistically, it's a turbulent plasma. But what you can very clearly see is that most of the power is on the positive omega side, which means that most of these fluctuations in this downstream window are moving to the left. They're moving away from the shock. And so traditionally, you would expect equal power on both sides. Here we've also included the alphane speed, but you would expect equal power on both sides. But what this is very clearly saying is that there is a preferential direction of the magnetic field downstream. And this is important because in the downstream region, because you've compressed those magnetic fluctuations, the alphane speed is now comparable with the downstream bulk flow. And so these two things are about equal, which means the assumption that the alphane velocity downstream is just whatever the bulk flow is not necessarily valid any longer. And so ultimately what we find is that the cosmic rays that make up the spectrum end up being isotropic in the wave frame rather than the bulk flow frame. And so here is a plot of the essentially the average cosmic ray velocity in the x direction. So it's the first moment above some value of the distribution, some injection momentum. And so what you would expect, or what has been expected, is that this value, the average velocity of the cosmic rays, should be 0 downstream. So these are taken in the downstream rest frame. But what we can clearly see consistently is that the cosmic rays also have a negative velocity downstream. And so what that says is the cosmic rays are moving away from the shock faster than the bulk flow plasma is. So essentially you have the stuff come in, gets processed by the shock, but the magnetic field has some kind of leftover inertia and it's continuing to travel away downstream and it's dragging the cosmic rays with it. And ultimately what this is going to do act as an energy sink for the downstream. And so you can go through and you can plot the amplified Alfvén speed in the downstream, and you can compare the cosmic ray velocity and the Alfvén velocity, and you get that the speed at which these the speed at which these cosmic rays are being dragged away is equal to the Alfvén speed, which is pretty encouraging because that's sort of how physics works. And so all this seems to be forming a consistent picture. So what you can do then is you can take the energy in cosmic rays, which are these pluses, and the energy, normalized energy in the magnetic field, and you can go through and you can include this extra Alfvénic drift term. You can include the fact that both cosmic rays and magnetic fields are escaping from the shock faster than is to be expected. And you can get a new prediction for the compression ratio. And so this is basically a 2D plot of the modified Rankine-Hugoniot jump conditions to include this extra effective Alfvénic drift. And you can see that even for a very small magnetic field or a very small cosmic ray efficiency, most of these values are above 4, which is denoted by this lime green line. You can see that it takes almost nothing to really increase the total compression ratio. And in fact, we can take these values in our simulation, feed them into the modified jump conditions, and we can get a prediction. So here's a plot in time of the compression ratio of our shock, these values, versus time based on this black line and the error bars associated with the prediction for the new Rankine-Hugoniot jump conditions. And what you can see is there's actually pretty good agreement. And I want to take a moment to emphasize that if you just do this without including the Alfvénic drift, but just the standard cosmic ray modified shock theory, which is this black dashed line, they don't really agree well at all. But once you include the effective Alfvénic drift, you get this more accurate compression ratio. So then this leaves us with, okay, so what about the slips? Well, we talked about before about how this Q value of the power law index really depended on the compression ratio. But now essentially what we have is this extra term on the bottom, which is going to correspond with the fact that less cosmic rays are making it back towards the shock. And essentially the probability of remaining is a little bit smaller than we expected because they're being convected away. So you can go through, you can use this new prediction for the power law spectrum. And what you can see, we make the same stat plot, is that before we had pretty poor agreement, but now we have quite remarkable agreement throughout the entirety of the simulation. So in conclusion, the main ideas of this talk and what we've really found is that shock simulations show evidence of cosmic ray modified shocks, that all this energy goes into these particles, and these particles can have kind of interesting feedback on the shock itself. We've showed that while we see cosmic ray modified shocks, this nonlinear DSA theory incorrectly predicts flatter spectrum when in fact we see an observation steeper spectrum, which is consistent with observations. And we found that the resolution to this tension between observations and modified shock theory essentially comes from the enhanced magnetic fields. And I want to take just a moment to kind of emphasize this really important point that kind of comes out of this. Because we talked about briefly that those magnetic fluctuations that showed up in the movie before were essentially driven by the cosmic rays, that you get a cosmic ray streaming instability, which produces magnetic fluctuations. And then these magnetic fluctuations compress and are actually going to take the cosmic rays out of the shock faster. And so what this means is there's this self-regulating process in which the compression ratio gets larger, you try to dump more energy into cosmic rays, the cosmic rays amplify larger magnetic fields, the larger magnetic fields reduce reduce how much energy can go into the cosmic ray spectrum, and by making this slope flatter. So we found that this is a self-regulating process for particle energization. And it also shows something that I really like to emphasize in kind of more astrophysical context, which is the fundamental importance of kinetic plasma physics to our understanding of these kinds of systems. Because if you tried to do a fluid model, you wouldn't necessarily be able to see this. So obviously there's a good bit of future work. I need to look at more Mach numbers, which I've started doing. I very obviously need to change the flow and field orientation, whether you're looking at a parallel shock or a perpendicular shock. Eventually the kind of goal of this is to try to use these simulations and this theory to compare and constrain with shock observations. I'm working with a graduate student at University of Chicago And we have some pretty exciting results as far as that go, where this kind of approach is really leading to pretty excellent agreement with observations. And then obviously this shows the importance of turbulence in the shock simulations. And so looking more at external turbulence is probably quite important to really understanding this problem well. And so with that, I will say thank you. I will check the time to see how much I went over. Oh no, pretty good. Okay, yeah. Thank you.
Thank you very much, Colby. That was a enlightening set of slides and a coherent presentation. If people have questions, this is the please submit them via the Q&A button that should be at the bottom of your Zoom screen. As we wait for people to populate that, you already started answering the first question I was going to ask Colby on the field flow orientation angle. Based on our understanding of kinetic, Weibull, and two-stream instabilities, do you expect to see differences in this self-regulation just based on the linear theory for those instabilities?
That is a great question. And to be honest, I don't know. All I know is that if you make the angle a bit too sheer without introducing more turbulent fluctuations, it's possible to kind of to basically choke out the rate at which particles are accelerated. Although there's also work to kind of assert that if you have the appropriate amount of turbulent fluctuations, that you can actually accelerate much more quickly with a perpendicular shock. But that being said, I have not looked at the linear theory aspect, because typically the way we think about these fluctuations upstream. So are you asking about the upstream or downstream fluctuations?
I'm talking about the instabilities that are being driven by the streaming of the cosmic rays.
So it is my impression right now that essentially all of the streaming that people believe is important for driving these is parallel streaming. And so if you make the inclination between the shock and the magnetic field different, it doesn't really change the growth rate of those, because the energetic particles will continue to just stream along field lines.
Okay.
Yeah.
Okay.
But that goes into whether it's the resonant instability or the non-resonant instability and all this different growth rate stuff. But I think the consensus is that it's a parallel streaming, and so the inclination doesn't change much.
Okay.
How do I look and see more? Chat.
I think we have both a chat and a Q&A.
Oh, thanks, David.
Are there other questions that people have had from this discussion?
Yeah, and I should say this is a weird format. It seems to be working well, but it's a weird format. So if you have a question and you don't feel like asking it in front of everyone on Zoom, I really encourage you to please feel free to email me. I'm always excited to talk about this stuff, and in that way, yeah, if this is useful at all, please feel free to email me. I imagine my email is somewhere on an email announcement or something, right?
And if not, if you're unable to find it via Google, I can also pass it along to anyone who's interested.
Perfect. Yeah.
We have a new question. I was wondering if you could say more about how you initialize the magnetic field in your hybrid simulations.
Sure. So this is a. So can you guys see all the windows I have up? Or maybe Chris, you're a good person to answer this.
By windows you have up, all I can see is your final slide.
Okay, great. So you can't see the questions and answer stuff. Okay. So the way the magnetic field is initialized is you essentially take a giant box and all you do is you say the magnetic field everywhere in this box is equal to 1 and pointing to the right. And that's it. So you don't have to seed any magnetic field or anything like that. That comes naturally from the instabilities from the shock. So I don't produce these kind of pretty fluctuations that you see, which really need to be there to actually reflect the particles, either downstream or upstream. I hope that answers. It might be a question about what is happening at the wall, and I cannot remember. It's in the paper. The relativistic hybrid dHybridR paper. I forget if the magnetic field is fixed or if the first derivative is fixed. It's one or the other.
So is there also anything driven by Pick noise, or contributing to the magnetic field, or is that a much lower order than the instabilities?
That is a good question. So the instabilities are much larger than the Pick noise, and you can kind of see them. We could go back to this other. Essentially, the instability comes from the Pick noise, which is really counting statistic noise. The magnetic field doesn't. The magnetic field basically starts with noise to machine precision, but then the variables of the variable fluctuating flows produce essentially noise in E very quickly, which produces noise in the magnetic field. For the particles that we're using, it's probably 1 part in 100 is the level of noise, but the actual instability swamps that very quickly, which you can kind of see in this. I mean, so if we go back, can I pause this? I think I can, yeah. So if you go back, you can see the far right, there hasn't been any signal that's really reached that there. So this would be noise, and then this would be instability. So it kind of, you know, and then this goes back to the first question too, where this is actually done in the simulation frame. So the wall is sitting there, and you can see stuff kind of moving to the left.
Okay. Are there any other questions? Oh, I think another one just popped up. Dimensionality of the simulations, 2D, 3V?
Yes, so these that I showed are, yeah, 2D in real space, 3D in velocity space. So we keep Vx, Vy, Vz, which means we can keep Bx, By, Bz, and Ex, Ey, Ez. So we have 3D simulations, but they're much more clunky, much harder to use, much harder to make pretty movies of. But that's something we've been considering too, because obviously you can't always trust 2D simulations. And Emily asked a great question, which is, are these results published? And I wanted to emphasize that these will be published in the next week or so. So we have, this is going to be essentially a set of 2 papers. One that really goes into how these magnetic fields modify the hydrodynamics. And the second paper is how the modified hydrodynamics in the magnetic field affect the power law spectrum. So we have the hydrodynamics bit written, ready to go, and then Damiano is writing the other paper, and that should be done in the next week or 2. But if you're interested, send me an email and I'll send you a link when it's up on archive, excuse me. Did I answer all of that?
I think so.
Published soon, I hope. It's got to be published soon. I'm leaving Chicago, so gotta finish it before I go.
If there are no other questions, let's thank Colby again. We got to figure out how to.
I'll do it for free.
Thank you very much. We hope to be hosting more of these sessions virtually until we can meet in person again. For those who weren't able to make it to all of this talk, it should be posted on the TAP YouTube channel in the not too distant future. So thank you all for joining, and see you either in person or virtually soon. Cheers.
Thanks again, guys. Bye.